Hello, and welcome to this presentation, Understanding Cable Phase Stability. In this presentation, we'll provide a short technical introduction to why cable phase stability is important and how the phase stability of coaxial cables is measured using vector network analyzers. An ideal coaxial cable would have the same attenuation and phase characteristics under all circumstances. In particular, the properties of the cable would not change with ambient temperature and would not change when the cable is moved or bent. And if these characteristics were to change, an ideal cable would return to its original characteristics after being moved or bent. That is, any changes would not be permanent. Although resistance to changes in attenuation is desirable, resistance to changes in phase is the more important characteristic for many modern applications. This resistance to change in phase is commonly called phase stability. Phase stability is important in many applications, including radar, satellite communications, and medical imaging. Phase stability is also important for some test and measurement applications, in particular the cables used when making measurements with a VNA, or vector network analyzer, since measuring phase is the vector part of a VNA measurement. It should also be noted that although we're rather broadly using the term cable in this presentation, as a practical matter, phase stability is a function of the entire cable assembly, and this includes any adapters and/or connectors as well. Another thing to keep in mind is that phase stability becomes more difficult to achieve as operating frequency increases. This is primarily due to the fact that shorter wavelengths are more sensitive to smaller structural changes in the cable. And it's also worth mentioning that the difference between a cheap and an expensive RF cable is often the cable's phase stability. Many higher-end cable manufacturers differentiate their products by using different manufacturing techniques to improve phase stability. As mentioned earlier, cable phase stability is affected both by temperature and by flexion, or the amount of bending. So let's take a closer look at each of these, starting with the impact of temperature. When the ambient temperature of a coaxial cable changes, the cable will also change in two main ways. The first is that the different components of the cable, that is the outer shield, the inner conductor, and the dielectric, will expand or contract. Because these are made from different materials, the amount or proportion of this expansion or contraction is different for each component. Since the impedance of a cable is determined in part by its geometry, expansion and contraction due to temperature will also change the cable's impedance. In addition to changing the cable's physical dimensions, temperature changes can also change the dielectric constant of the insulating material itself, and this can have a significant impact on the cable's properties. Phase changes caused by temperature are often expressed or graphed as a change in parts per million as a function of frequency. Remember, too, that coaxial cables are often used in harsh and/or outdoor environments, where large changes in temperature may be both more common and more severe compared to an indoor or lab environment. That said, even moderate temperature changes, such as those found in indoor environments, can affect phase stability, and a common example of this is the so-called PTFE knee. PTFE, polytetrafluoroethylene, more popularly known as Teflon, is widely used in coaxial cables, both for the outer sheath or jacket, but more importantly for the dielectric or internal insulation, since PTFE has many desirable properties. And although a wide operating temperature range is one of those desirable properties, the electrical properties of PTFE cables do change as temperature changes. In particular, these types of cables exhibit an abrupt phase change, or knee, at room temperature, that is, at around 15 to 25 degrees Celsius, or about 60 to 80 degrees Fahrenheit. This PTFE knee, or Teflon knee, is seen in cables with both a solid PTFE core and in cables with a more foam-like PTFE core. Recall that high-end cable manufacturers often differentiate their products based on phase stability, and thus there are various manufacturing methods, such as modifying the composition of the dielectric, that can be used to minimize the effects of this PTFE knee. Next, let's look at the effect of flexion, also sometimes called flexure, on phase stability. As discussed earlier, physical bending of a cable can lead to changes in both the amplitude and phase behavior of that cable. This is primarily because, like temperature changes, bending a cable also changes its physical geometry, that is, the relative positions of the dielectric, shield, etc. And this in turn can change the impedance at different points along the cable. Although we often talk about the impedance of a cable, it's good to keep in mind that impedance is a point concept, and that the impedance of a cable can change at different points along the length of the cable. Note too that semi-rigid cables are sometimes used in applications that require high phase stability, in part because these cables are bent only once during installation, after which their geometry remains mostly constant. Another important observation is that bending near the connectors at the ends of the cables can create much greater challenges than bending which occurs in the middle of the cable. And this is one reason why high-quality cables often have a thicker sheath near the ends of the cable, since this helps to prevent excessive bending near the connectors. Phase stability during flexion is very important for cables that are frequently moved. This movement may be intentional, such as in test and measurement applications, where the cables must be connected to and disconnected from the device under test. But unintentional movement can also occur, for example when a cable is subject to mechanical shock and/or vibration. One danger when it comes to flexion is that cables may not fully recover to their pre-bending state. That is, the characteristics of the cable change both while the cable is being bent, but may also persist after bending. It's therefore important to measure or quantify both of these states. Cable phase stability is also important in the case of cables that are moved or bent only once, for example during the installation or setup of a system. Any movement of a static or fixed cable has the potential of reducing the effects of any calibration or error correction that might have been applied during its installation. Let's take a few moments to talk more about phase stability in test and measurement applications. When working with VNAs, it's very common for test cables to be moved, curved, or bent, particularly during test setup. Once the setup has been completed and calibration has been performed, it's a good idea to try to minimize the movement of these cables. Sometimes adhesive tape is used to fix the cable to the test bench. But it's difficult to completely eliminate any chance of cable movement. Because of this, the cables used in test and measurement applications should be high quality, and a phase-stable cable is very important in ensuring both accurate and repeatable measurements. You may hear these kind of cables called metrology-grade cables. One additional advantage of using phase-stable cables is that they can reduce the need for frequent recalibration, which in turn reduces time and effort. With regards to temperature, resistance to phase changes is less important in a lab environment, but it may become important when a device under test needs to be tested under a range of temperatures in a temperature chamber. Evaluating cables for phase stability versus temperature is also performed using a temperature chamber. Here, the device under test is the cable itself. Typically, the cable is placed in the chamber in loose coils. Loose here means coils that are much larger than the cable's minimum bending radius. The cable is then soaked at each temperature for a period of time, usually tens of minutes, and the resulting phase shift is measured with a vector network analyzer. Results are then plotted as phase shift or variation as a function of temperature. Temperature tests are performed at a fixed frequency, but may also be repeated at different frequencies as well. Here's an example measurement of phase variation as a function of temperature. -20 is used as the temperature for the reference phase, and we see that at 1 GHz, phase variation increases by a few degrees up to about +20 Celsius, and then remains roughly constant. Similar behavior is seen at 2 GHz, 3 GHz, 4 GHz, and so on. The set of traces shown here is typical in that phase variation tends to increase with both increasing temperature and increasing frequency. Next, let's look at how to measure cable phase stability as a function of flexion or bending. At a high level, this is done by creating a known or controlled amount of flexion and then measuring the variation using a VNA. We'll go into much more detail on this shortly. Results are plotted as phase shift as a function of frequency, and typically phase shift is on the order of single-digit degrees. There are also several variations in how these tests can be performed. For example, the test may be repeated with different bend radii. The effect of repeated bending can also be investigated. That is, does a cable show greater or less phase variation when it's bent for the 10th, 100th, or 1000th time? And as we mentioned earlier, it's important to know if the cable returns to its starting phase values after being unwrapped or unbent. This is sometimes called phase recovery. It shouldn't be surprising that phase change increases with increasing bending, and this is often a linear or a quasi-linear relationship. The smaller or tighter the cable bend radius, the greater the amount of phase change that's introduced by this bend. There are 3 general methods for testing phase stability under flexion using a VNA. These are so-called shake stability, reflection-based measurements, and transmission-based measurements. We'll start by taking a brief look at shake stability. As the name implies, shake stability testing involves manually moving or shaking a cable. Here, one or both ends of the cable are connected to the VNA, and the trace is examined for phase variations while the cable is being manually manipulated. This kind of testing can provide a very quick check of cable phase stability and is mostly used to identify defective cables and/or cables with very serious stability issues. It can also be used to detect loose or insufficiently tightened connections. However, this method is both very unscientific and not reliably repeatable, and thus cannot be used to numerically quantify a cable's phase stability. In a reflection stability test, the cable is attached to the VNA at one end, and the far end is terminated with a short. The cable is first placed in a reference position, that is, with the cable fully extended in a straight line, and a one-port normalization is performed. After this, the cable is bent around a mandrel, which provides a stable and reproducible bend. In most cases, this bend is either 180 degrees or 360 degrees. Mandrels with different radii can be used, and in many cases the measurement is repeated with the cable bent in the other direction. Note that when using this methodology, the measured phase variation must be divided by 2 in order to account for the fact that the signal travels out to the short at the end of the cable and then is reflected back to the source. Phase variation due to flexion is normally plotted as a function of frequency. Here, the blue trace shows phase variation when the cable under test is wrapped 180 degrees around a mandrel with a diameter of 8 centimeters. Note that the phase shift in this case is both low, a few degrees, and is also relatively constant over the measured frequency range. Wrapping the same cable around a mandrel with a smaller diameter increases the phase shift, and this effect becomes even more pronounced at higher frequencies. This behavior is very common among many types of cables when the bending radius and/or frequency are increased. Phase stability can also be measured using a transmission test. Here, both ends of the cable are connected to ports on the VNA, a 2-port normalization is performed, and then a transmission measurement is run. As before, a mandrel is used to accurately and reproducibly create the desired bend radius. In transmission stability measurements, the cable is typically curved either halfway around the mandrel, as shown here, or completely around the mandrel one time before being connected back to the VNA. The phase variation resulting from this flexion can be read directly from the VNA trace. There is no need to divide the result by 2, as we did when making reflection measurements. Let's end with a brief summary. The term phase stability refers to how the phase characteristics of a cable change with changes in temperature and/or flexion. Good phase stability is important in many applications and is one of the main reasons for the cost of high-quality RF cables. Phase stability is measured using VNAs or vector network analyzers. With regard to the effect of temperature on phase stability, this is tested by placing the cables in a temperature chamber and measuring phase variation at different temperatures. There are numerous methods for measuring the effects of flexion on phase stability, and a mandrel is used to create a known and reproducible amount of bending. The phase shift in a wrapped cable can be measured in either reflection or transmission mode, and the results are plotted as phase shift versus frequency. This concludes our presentation, Understanding Cable Phase Stability. If you'd like to learn more about cable testing, VNA measurements, or vector network analyzers from Rohde and Schwarz, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.